Hi, welcome to Maths&Tricks. Today I will show you how to find an eigenvalues in its vector using the power method. Well, the method is simple and straight, and we know very well how to figure it out. But the mystery behind most of the mathematical expressions and solutions is that why we do this and where we need to use it. Certainly, I don't know the answer because nobody told me in my math class. I can't solve this mystery, but rather this will help you for your exam preparations. Now, to understand the physical interpretation of eigenvalues, let's see what this man says.
To most physicists, I guess, lambda probably means the length of a wave. It means how long is the distance between one peak of a wave and the next one. Very easy to understand, water waves traveling along a pond. But to many engineers, and particularly people who do dynamics, lambda means an eigenvalue. It's a special value, a special number that you get out of a matrix that tells you something very important about the nature of that matrix. The word is eigenvalue. Some people would call them proper values or characteristic values. It's a mixture of a German word and an English word, obviously, eigenvalue is. And I'm not sure what the exact literal translation is, but it means a special number that characterizes the matrix. And if you have a matrix that is 10 by 10, that has 10 rows in it and 10 columns of numbers in it, it will have 10 eigenvalues. People often ask, well, what physical significance can there be to eigenvalues? And I can show you two very simple instances of that. One has to do with vibration, and if I cantilever this ruler off the side of the bench and excite it with some initial condition, then you see that the ruler goes into an oscillation, and the oscillation gradually dies away. And we see two different parts to the vibration of this ruler. One is the oscillating part, which has a certain frequency, and I'm going to guess that that's about 4 times per second, about 4 hertz. But also you see the decay part, that the oscillations are getting smaller and smaller and smaller as we go through time. And the lambda has both of those parts built into it. So there's one good example. This is a very simple structure. In engineering, we have to analyze very complex structures that have excitations, not just some giant person flicking the end of the structure, but they have sinusoidal excitations from motors turning and from loads moving backwards and forwards that, if they hit an eigenvalue, really will shake that structure to bits. And a second physical application for eigenvalues is also demonstrable with a ruler, and it's the buckling load of a ruler. Now, if you stand the ruler up vertically, you can put a certain amount of weight on the top of it, and it will stay perfectly steady. And as you increase the amount of weight, and I'm doing this with my hand, it will remain steady until you come to a certain point, and it's just happened here, where the load is just too much for the ruler to bear. And that particular load is called a critical load, or a buckling load for the ruler. And you find that out by doing a calculation, which is an eigenvalue problem. I know of one other application that probably everybody in England uses eigenvalues every single day, and that is the Google search engine. It formulates its search problem as a giant eigenvalue problem with a matrix that probably, I'm guessing, has millions of rows and millions of columns, sparsely populated, not a number in every single place, and it calculates the eigenvalues of this huge matrix and uses that to determine which entries should it show you first.
Thank you, sir, for sharing these nice information. So let's see an example now. If A is a new matrix of a linear system, and to find the maximum eigenvalues in its vector. The first step is to multiply this matrix A with some initially guessed vector x naught, for instance, -1, 2, and 1. Use your calculator to multiply these two matrices and take common the maximum value from the resultant matrix, which is 8 in this case. So this was the first iteration. The eigenvalue is 8 and the vector is x1. In the next iteration, multiply the same matrix A with vector x1. So take the maximum value, which is 4.75, is a common, and we left with vector x2. Use this vector for the third iteration and so on. Now let me show you how to use calculator in matrix mode. So in the third iteration, the maximum eigenvalue, which is approximately 5, and the vector x3, and finally we get a closed value 5.118 and the vector x5 and the sixth iteration. And as usual, thanks for watching.